Close your eyes. Place your hand gently over your heart. Feel that steady rhythm. That quiet drumbeat that has been with you since before you were born. Lub-dub. 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 This is your body's most faithful timekeeper. More reliable than any clock on your wall. More constant than the sunrise. Your heart beats about 60 to 100 times each minute. Every single day of your life. But here's something wonderful and strange. That heartbeat of yours? It's not just marking time. It's actually traveling through time. Moving forward into the future at exactly 1 second per second. Just like everything else in our universe. Or so it seems. The truth is far more beautiful. And far more mysterious. Your heartbeat, your breath, your thoughts right now, they're all part of something much bigger. Something that would have seemed like magic to people just over a century ago. You see, time isn't what we think it is. It's not a river flowing at the same speed everywhere. It's not a metronome keeping perfect rhythm across the cosmos. Time is more like an ocean. Sometimes calm and steady. Sometimes flowing fast. Sometimes moving slow as honey. And you? You're swimming in that ocean right now. Every moment of your life, you experience something that scientists call time dilation. It sounds complicated, but it's really quite simple. Time dilation means that time can stretch. It can slow down. It can speed up. All depending on where you are and how fast you're moving. Right now, as you lie here listening to these words, time is flowing around you in the most natural way. Your cells are aging. Your hair is growing. Your fingernails are getting longer, bit by tiny bit. The Earth is spinning beneath you. The Moon is slowly moving away from our planet. The Sun is burning hydrogen into helium, deep in its core. All of this is happening in your personal bubble of time. But what if you could step outside that bubble? What if you could see time the way it really works? You'd discover something amazing. Time doesn't flow the same way for everyone, everywhere. A person standing on a mountain ages slightly faster than someone at sea level. Someone flying in an airplane experiences time differently than someone walking on the ground. And if you could somehow travel to Mars and live there, your body would age at a different rate than your friends back on Earth. These differences are tiny. So small you'd never notice them in a human lifetime. But they're real. They're measurable. And they're happening to you right now. Think about that mountain climber for a moment. Up there, where the air is thin and the view stretches for miles, gravity is just a little bit weaker. And where gravity is weaker, time moves just a tiny bit faster. The climber's watch would gain a few extra nanoseconds each day compared to yours. A nanosecond is unimaginably small. It's 1/1000th of a second. But it's there. It's real. It's measurable with the right instruments. This isn't science fiction. This is science fact. The same science that makes your GPS work. The same science that helps satellites find you when you're lost. The same science that proves something incredible about our universe. Time is alive. It breathes. It flows. It dances. And you're part of that dance. Your heartbeat is marking time in your own personal reference frame. That's what scientists call your unique experience of time and space. From your reference frame, lying here right now, everything seems normal. Your clock ticks at normal speed. Your thoughts move at their usual pace. Your heart beats its familiar rhythm. But someone moving very fast compared to you would see something different. To them, your heartbeat would appear to slow down. Your thoughts would seem to move like thick syrup. Your clock would appear to tick more slowly. And here's the beautiful part. You wouldn't feel any different. From your perspective, everything would be completely normal. It's only when you compare your experience to someone else's that the magic reveals itself. This is what Albert Einstein discovered over 100 years ago. he realized that time and space are woven together like threads in a cosmic fabric. Move through space, and you change your movement through time. Get close to something very massive, and gravity stretches time around you. The faster you move through space, the slower you move through time. It's one of the most elegant truths in all of science. And it's happening to you, in tiny ways, every moment of your life. When you walk across a room, you experience time dilation. When you ride in a car, you experience time dilation. When you travel in an airplane, you experience more time dilation. The effects are incredibly small, but they're there. Your body is a time machine. Not in the way you might imagine from movies, but in the real, scientific way. Every step you take moves you through space-time. Every heartbeat carries you forward through the fourth dimension. And that brings us to something wonderful to think about. If small movements create small changes in time, what would happen with big movements? What if you could travel very fast? What if you could visit places where gravity is much stronger or much weaker than Earth? What if you could take a journey to Mars? The red planet waits out there in the darkness, spinning slowly on its axis. Its gravity is weaker than Earth's. Its days are a little longer than ours. And if you could somehow make that incredible journey, time itself would flow just a little differently for you. Your heartbeat would still feel the same to you. But compared to someone back on Earth, something subtle and beautiful would change. You would be swimming in a slightly different current of the ocean of time. And as you drift toward sleep tonight, your heart keeping its faithful rhythm, remember this. You are already a time traveler. You've been traveling through time your entire life. 1 second per second, one heartbeat at a time. But the universe holds deeper mysteries about time and space, waiting to be explored. What would it feel like to experience time flowing differently? What did a young scientist with wild hair discover about the nature of reality itself? Picture a young man in Switzerland over 100 years ago. His name is Albert Einstein. He's 26 years old. His hair refuses to stay neat, no matter how much he tries to comb it. He works at a patent office, looking at inventions all day long. But his mind? His mind wanders to the stars. In the evenings, Albert takes long walks through the quiet streets of Bern. He watches trains pull into the station. He sees their lights cutting through the darkness. And he begins to wonder about something that no one has ever wondered about before. What if time isn't the same for everyone? For thousands of years, humans believed time was like a great river, flowing at the same speed everywhere, moving forward at exactly the same pace for every person, every planet, every star in the universe. This seemed so obvious that no one questioned it. But Albert Einstein was different. He had a gift for seeing what others couldn't see, for asking questions that others were afraid to ask. One evening, as he walked home from work, he imagined something strange. What would happen if he could run beside a beam of light? What would he see? How would the world look if he could somehow keep pace with light itself? This simple question would change everything we know about reality. You see, light is special. It moves at the same speed no matter what. Whether it comes from a flashlight in your hand or from a star a million miles away, light always travels at exactly the same pace. About 186,000 miles per second. That's fast enough to circle the entire Earth 7.5 times in just 1 second. Scientists had measured the speed of light. They knew it was constant. But they didn't understand what this meant. They didn't realize that this simple fact would unlock the deepest secrets of time and space. Einstein realized something remarkable. If light always moves at the same speed, then something else has to change. Something we thought was permanent and unchanging. Time itself. Imagine you're standing on a train platform at night. A train rushes past you, its windows glowing with warm yellow light. To you, standing still, the train appears to be moving very fast. But to someone sitting inside the train, reading a book, everything feels perfectly normal. They're not moving at all, from their point of view. The world outside is moving past them. Now imagine that same train, but moving at nearly the speed of light. Something incredible would happen. From your perspective on the platform, time inside the train would slow down. The passengers' movements would become like slow motion. Their clock would tick more slowly. Their thoughts would move like honey. But here's the beautiful mystery. The passenger wouldn't feel any different. To them, time would flow normally. Their clock would tick at its usual pace. Their thoughts would move at their normal speed. It's only when you compare their experience to yours that the magic reveals itself. This is what Einstein discovered. Time is not a river flowing at the same speed everywhere. Time is relative. It depends on how fast you're moving and where you are in the universe. Einstein called this his special theory of relativity. The word relativity means that time and space are relative to your point of view. Your reference frame. Your unique experience of the universe. At first, other scientists didn't believe him. The idea seemed too strange. Too impossible. How could time itself change? How could something so fundamental, so basic, be flexible? But Einstein had mathematics on his side. Beautiful equations that showed exactly how time would stretch and bend. And slowly, as other scientists studied his work, they began to see that he was right. The universe was stranger and more wonderful than anyone had imagined. Einstein didn't stop there. He kept thinking, kept wondering. What about gravity? What about massive objects like planets and stars? How do they affect the flow of time? This led to his general theory of relativity. An even more beautiful and surprising discovery. Einstein realized that massive objects don't just pull on other objects with gravity. They actually bend space and time itself. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a dip, a curve in the sheet. Now imagine rolling marbles across the sheet. They would naturally curve toward the bowling ball, following the bent shape of the sheet. This is how gravity works. Massive objects like the Earth and the Sun create curves in the fabric of space-time. Other objects, including light itself, follow those curves. And here's the most amazing part. In those curved regions of space-time, time flows differently. Where gravity is stronger, time moves more slowly. Where gravity is weaker, time moves more quickly. This means that your feet, closer to the Earth's center, age slightly more slowly than your head. The difference is tiny, impossibly small, but it's real. Einstein's discovery seemed like pure theory at first. Abstract mathematics with no practical use. But today, his insights make modern life possible. The GPS in your phone? It works because of Einstein's relativity. The satellites orbiting Earth experience time differently than you do down here on the surface. Without accounting for this time difference, your GPS would be wrong by several miles. The atomic clocks that keep perfect time around the world? They have to be adjusted for relativity effects. Time really does flow differently at different heights and different speeds. Einstein showed us that the universe is far more flexible and mysterious than we ever imagined. Space can stretch. Time can slow down. Massive objects can bend the very fabric of reality. But the most beautiful part of Einstein's revolution wasn't just the science. It was the way he thought about the world. With wonder. With curiosity. With a willingness to question everything, even the most basic assumptions about reality. He looked at trains and saw the secrets of time. He looked at gravity and saw the curvature of space itself. He looked at light and discovered that it holds the key to understanding everything. As you lie here in the quiet darkness, think about that young man with the wild hair. Think about how one person's curiosity changed our understanding of everything. How questions that seemed silly or impossible led to the most profound truths. And remember that the same universe Einstein explored surrounds you right now. The same mysterious forces that bend time and space are gently at work in your own life. But there's something even more remarkable about the speed of light, something that makes it the cosmic speed limit of our universe. In the quiet darkness of your room, light dances all around you. Gentle photons from distant streetlights slip through your curtains. The soft glow from your clock face carries light across the space to your eyes. Even in what seems like complete darkness, light is there. Moving. Dancing. Following the most sacred rule in our universe. Light always moves at exactly the same speed. This might sound simple. Almost boring. But this one fact is the key that unlocks the mystery of time itself. Imagine you're sitting by a calm lake at sunset. The golden light from the sun touches the water and bounces toward your eyes. That light has traveled 93 million miles from the sun's surface. It has crossed the cold emptiness of space. And every single mile of that journey, it moved at exactly 186,000 miles per second. Not a little faster. Not a little slower. Always exactly the same speed. Now imagine a friend throws a ball to you across that same lake. The ball starts fast, then slows down as gravity pulls on it. The air pushes against it. By the time it reaches you, it's moving much slower than when it left your friend's hand. But light? Light never slows down. Light never speeds up. Light moves through empty space at one speed, and one speed only. Scientists call this the speed of light, and they use the letter c to represent it. Why is this so important? Because light doesn't care what you're doing when you measure its speed. Here's what that means. If you're sitting perfectly still and you measure the speed of light, you'll get 186,000 miles per second. If you're running as fast as you can and you measure the speed of light, you'll still get 186,000 miles per second. If you're flying in a jet plane, riding in a rocket ship, or somehow zooming through space at incredible speeds, light will still pass you at exactly 186,000 miles per second. This seems impossible. It goes against everything we experience in daily life. When you're riding in a car and another car passes you, that car appears to be moving slowly compared to you. When you're walking and someone runs past you, they don't seem to be running as fast as they would if you were standing still. But light breaks this rule. Light doesn't care how fast you're moving. It always moves past you at the same speed. Einstein realized that this means something incredible about our universe. If light always moves at the same speed no matter what, then something else has to change to make this possible. Space and time themselves must be flexible. Think of it like this. Imagine you're stretching a piece of taffy. As you pull it, it gets longer and thinner. The taffy changes shape to accommodate the stretching force. Space and time work like that taffy. When you move very fast, space contracts and time stretches. This allows light to maintain its constant speed relative to you. The faster you move through space, the more time slows down for you. The closer you get to the speed of light, the more dramatic this effect becomes. But here's something beautiful. You would never feel this happening. From your perspective, everything would seem completely normal. Your watch would tick at its usual pace. Your thoughts would flow at their normal speed. Your heart would beat its familiar rhythm. It's only when someone else watches you from far away that they would see time moving differently for you. Scientists have proven this in amazing ways. They've taken identical atomic clocks and put one on a fast airplane while keeping the other on the ground. When the airplane returns, the clocks show slightly different times. The clock that traveled fast has fallen behind, just as Einstein predicted. The difference is tiny. Just a few billionths of a second. But it's real. It's measurable. And it proves that time really does slow down when you move fast. This means that light is more than just illumination. Light is the cosmic speed limit. Nothing in the universe can move faster than light. Not rockets, not particles, not information, not anything. But why? What makes light so special? Light has no mass. Photons, the tiny particles that make up light, weigh absolutely nothing. This allows them to move at the maximum possible speed through space. They don't need to accelerate. They don't need fuel. They simply exist at the speed of light. Everything else in the universe has mass. You have mass. Planets have mass. Spaceships have mass. And mass makes it harder and harder to go fast. The closer you get to the speed of light, the more energy it takes to go even faster. If somehow you could approach the speed of light, something amazing would happen. Your mass would seem to increase from the perspective of someone watching you. You would become harder and harder to accelerate. It would take more and more energy to make you go faster. At exactly the speed of light, it would take infinite energy to accelerate you. This is why nothing with mass can reach the speed of light. The universe simply won't allow it. But this cosmic speed limit creates something beautiful. It creates a universe where cause and effect work properly. Where information can't travel faster than it should. Where the laws of physics remain consistent everywhere. Light carries more than just brightness from place to place. Light carries information. The light from distant stars tells us what they're made of. The light from the sun brings energy that powers all life on Earth. The light bouncing off this page carries words to your eyes. And all of this happens at exactly the same speed, everywhere in the universe. It's like the universe has chosen one perfect pace for sharing information and energy across the vast distances of space. As you rest here in the gentle darkness, remember that light is flowing all around you. Through the walls of your room, carrying radio waves and Wi-Fi signals. From distant galaxies, bringing messages about the birth and death of stars. From the sun, even now on the other side of the Earth, racing through space to bring tomorrow's dawn. All of it moving at the same sacred speed. All of it honoring the cosmic speed limit that makes time dilation possible. But what does this mean for your own body? How does this constant speed of light affect the rhythm of your cells, your heartbeat, your very existence? Your body is the most beautiful clock in the universe. Not because it's perfectly accurate. Not because it never loses time. But because it carries within itself countless tiny timepieces, all working together in perfect harmony. Right now, as you lie here breathing softly, your heart is keeping time. Lub-dub, lub-dub, lub-dub. About 70 beats each minute. Each beat pushes blood through thousands of miles of vessels in your body. But your heart isn't the only timekeeper. Deep inside every cell, tiny molecular machines are spinning and working. Creating energy. Building proteins. Copying DNA. Each process happens on its own schedule. Some take milliseconds. Others take minutes or hours. Your brain cells fire in rhythmic patterns. Your liver processes toxins on a 24-hour cycle. Your skin cells replace themselves every few weeks. Your bones rebuild themselves over months and years. All of these biological clocks are ticking away inside you, creating the symphony of life. The gentle rhythm that makes you, you. Now imagine something wonderful and strange. Imagine that all of these clocks, every single one, could slow down together. Not because you're sick or tired. Not because something is wrong. But because of the fundamental nature of space and time itself. This is what happens when you move very fast. All the clocks in your body slow down by exactly the same amount. Your heartbeat slows. Your brain waves slow. Your cells' molecular machines slow. Even your thoughts slow down. But here's the beautiful part. You wouldn't feel any different. From your perspective, everything would seem completely normal. Your heart would feel like it was beating at its usual pace. Your thoughts would seem to flow at their normal speed. It's only someone watching you from far away who would see the change. To them, you would appear to be moving in slow motion. Like a film played at half speed. Your gestures would be languid and dreamy. Your words would sound deep and stretched out. Scientists call this time dilation. The stretching of time itself. And it happens to you every single day, in tiny ways you never notice. When you walk across your room, you experience a tiny bit of time dilation. Your body's clock slowed down by an impossibly small amount. So small that even the most sensitive instruments can't measure it. But it's there. It's real. When you ride in a car, the effect is slightly bigger. When you fly in an airplane, it's bigger still. The faster you move, the more time slows down for you. But these everyday speeds create such tiny changes that they don't matter for normal life. To notice real-time dilation, you'd need to move at a significant fraction of the speed of light. Imagine you could somehow travel at half the speed of light. About 93,000 miles per second. At that incredible speed, something amazing would happen to your personal time. To someone watching from Earth, your biological clocks would slow down significantly. Your heartbeat would appear to slow. Your movements would seem graceful and dreamlike. A year of your life would pass while more than a year passed on Earth. But to you, riding in your impossible spaceship, everything would feel perfectly normal. Your heart would seem to beat at its usual rhythm. Your thoughts would flow at their normal pace. Your watch would tick normally. You would be living in your own bubble of slowed time. Your own reference frame, where the laws of physics work exactly as they always have. This isn't just theory. Scientists have seen this happen with tiny particles called muons. These particles are created high in Earth's atmosphere when cosmic rays hit air molecules. Muons normally decay, disappearing very quickly. They should break apart before they reach the ground. But muons created in the upper atmosphere are moving very fast, close to the speed of light. Time dilation slows down their internal clocks. Their decay process slows. This gives them enough time to reach the surface of the Earth, where scientists can detect them. In a way, these muons are time travelers. They live longer than they should because they're moving fast through space. Your body could do the same thing, in principle. If you could somehow travel at nearly the speed of light, you would age more slowly than people back on Earth. Your cells would divide more slowly. Your hair would grow more slowly. Your fingernails would grow more slowly. Everything about your biology would slow down by exactly the same amount. This means that motion through space affects motion through time. The faster you move through the 3 dimensions of space, the slower you move through the 4th dimension of time. Think of it like walking across a field. If you walk straight north, all of your motion is in the north direction. But if you walk northeast, some of your motion is toward the north and some is toward the east. You can't go as fast in the north direction because some of your energy is being used to go east. Space and time work similarly. All objects in the universe are always moving through space-time at the speed of light. If you're sitting still in space, all of your motion is through time. You move forward through time at the normal rate. But if you start moving through space, some of your motion through space-time gets diverted from time into space. You move more slowly through time because you're moving through space. The faster you move through space, the slower you move through time. It's like a cosmic trade-off. A fundamental law of the universe. This affects every clock in your body. Your heart, your brain, your cells, your DNA. Everything that measures the passage of time slows down together. That's why you don't feel any different. You and all your clocks slow down by exactly the same amount. But time dilation isn't just about motion. There's another way to slow down time. And this other way is happening to you right now, as you lie here on the surface of planet Earth. The Earth's gravity is gently stretching time around you, creating a subtle, constant time dilation effect that touches every moment of your life. Your feet experience slightly different time than your head. The difference is tiny, but it's there. Gravity doesn't just pull on your body. It pulls on time itself. And this gravitational time dilation opens up even more beautiful possibilities for how time can stretch and flow. Imagine what would happen if you could visit a place where gravity is much stronger or much weaker than Earth's. How would that change the rhythm of your body's clocks? How would that affect your personal experience of time? What would it feel like to have your heartbeat keep a different rhythm, not because you're excited or calm, but because you're swimming in a different gravitational current of space-time itself? Imagine the softest silk scarf stretched perfectly flat. Now picture placing a heavy marble in the center. The scarf dips and curves around the marble, creating a gentle bowl shape. The silk bends because of the marble's weight. This is how Einstein saw gravity. Not as a force pulling things together, but as mass bending the very fabric of space and time. Right now, as you rest here, you're lying in one of these gentle curves. The Earth beneath you, with all its mass, creates a dip in space-time. You don't fall through the floor because the floor pushes back. But you're still resting in Earth's gravitational well. And in this well, time moves just a little bit slower than it would out in empty space. Your feet are deeper in this gravitational well than your head. They're about 6 feet closer to Earth's center. This tiny difference means your feet experience slightly stronger gravity than your head. And where gravity is stronger, time moves more slowly. So your feet age a little bit slower than your head. The difference is incredibly small. About 90 billionths of a second per year. But it's real. It's measurable. And it's happening to you right now. Think of gravity as creating invisible rivers of time. These rivers flow more slowly near massive objects and faster farther away. You're floating in one of these rivers, with your feet in slightly slower water than your head. The Earth creates a gentle time river around itself. The Sun creates a much deeper one. Massive stars create rivers so deep that time crawls like thick syrup. And black holes? They create waterfalls of time so steep that time nearly stops at their edges. But let's stay here on Earth for now. This gentle gravitational well that cradles our entire planet. Every mountain peak experiences time slightly faster than sea level. Every valley experiences time slightly slower. The difference is tiny, but it's there. Clocks on mountaintops run fast compared to clocks at the beach. Scientists have measured this with atomic clocks. These are the most accurate timepieces ever built. They can measure time differences smaller than a billionth of a second. When they take identical atomic clocks and place one on a mountain and one at sea level, the mountain clock runs faster. This happens because the mountain is farther from Earth's center. It sits in a slightly shallower part of Earth's gravitational well. Time flows a little faster there. GPS satellites orbit high above Earth's surface. Up there, about 12,000 miles above you, gravity is much weaker. Time moves faster for those satellites than it does for you down here. Without accounting for this time difference, GPS wouldn't work. The satellite's clocks would drift compared to Earth-based clocks. Your phone's GPS would be wrong by miles. Every day, scientists adjust for Einstein's gravitational time dilation to keep GPS accurate. This means that every time you use your phone to navigate, you're using Einstein's discovery about gravity and time. You're using the fact that time flows differently at different distances from Earth's center. But gravity's effect on time isn't just a curiosity for scientists. It connects you to the deepest mysteries of the cosmos. When you look up at the night sky, you're seeing light that has climbed out of gravitational wells. Light from the sun has climbed out of the sun's much deeper gravitational well to reach you. As it climbed, something beautiful happened. The light lost energy fighting against the sun's gravity. This made its wavelength stretch out, shifting its color slightly toward the red end of the spectrum. Scientists call this gravitational redshift. Every photon of sunlight carries within it the signature of its journey through curved space-time. The gentle warmth you feel from sunshine has been changed by gravity's pull on time itself. The same thing happens with light from distant stars and galaxies. As their light travels through the universe, it encounters gravitational fields. It climbs in and out of invisible wells of curved space-time. Each encounter leaves its mark on the light. By studying this light carefully, astronomers can map the gravitational landscape of the universe. They can find massive objects that don't emit light themselves. They can discover how matter is distributed across cosmic distances. Gravity's pull on time becomes a tool for exploring the universe. But perhaps the most beautiful thing about gravitational time dilation is how it shows us that time isn't separate from space. They're woven together into a single fabric. When mass curves space, it automatically curves time too. You can't bend one without bending the other. Space and time are like dance partners, moving together in perfect synchronization. This unified space-time responds to mass and energy like a living thing. It stretches and contracts. It ripples and waves. When massive objects move quickly, they send ripples through space-time itself. Scientists have detected these gravitational waves with incredibly sensitive instruments. The universe is singing to us through the medium of space-time itself. And that song includes the subtle variations in time's flow created by gravity. As you lie here, feeling the gentle pull of Earth's gravity holding you safely in place, remember that you're experiencing more than just weight. You're experiencing the curvature of space-time itself. The bending of the universe around the mass of our planet. Your body is floating in a river of time that flows at its own unique pace. Slightly slower than it would in empty space. Slightly different at your feet than at your head. You are living proof that time is not rigid or absolute. It's flexible, responsive, alive. It bends to accommodate mass and energy. It flows like water around the matter in the universe. And this opens up the most fascinating possibility of all. What if two people could experience very different flows of time? What would happen if one person stayed in a shallow gravitational well while another ventured into a much deeper one? Picture two sisters, born under the same starlit sky. Let's call them Emma and Stella. They enter the world together, their first breaths taken at the exact same moment. Their hearts beat in rhythm. Their cells divide at the same pace. They are perfect mirrors of each other in time. For 20 years, they grow up side by side. They celebrate the same birthdays. They age at exactly the same rate. Every wrinkle, every gray hair, every laugh line appears on both faces at the same time. Then, on their 20th birthday, they make different choices. Emma decides to stay on Earth. She loves the feeling of grass beneath her feet, the sound of rain on her roof, the comfort of familiar gravity. She builds a life in her hometown. She watches the seasons change. She grows older one day at a time. Stella dreams of the stars. On her 20th birthday, she climbs aboard a spacecraft capable of traveling at 90% the speed of light. She waves goodbye to Emma and launches into the cosmic dark, seeking adventure among distant suns. For the next 20 years, Emma lives her earthbound life. She watches sunrises and sunsets. She feels the pull of moon tides. She experiences every season, every weather pattern, every natural rhythm of her home planet. Meanwhile, Stella races through space at incredible speed. She visits distant star systems. She sees planets with purple skies and triple suns. She witnesses cosmic phenomena that no human has ever seen before. But something subtle and beautiful is happening during their separation. Something that would have seemed like magic before Einstein. Time is flowing differently for each sister. Emma, resting in Earth's gentle gravitational well, experiences time at its normal earthly pace. Her biological clocks tick steadily. Her heart beats about 70 times per minute. Her cells divide on their usual schedule. 20 Earth years pass for her, one day at a time. But Stella, racing through space at 90% the speed of light, experiences something extraordinary. From her perspective, everything feels completely normal. Her heart seems to beat at its usual pace. Her thoughts flow naturally. Her watch ticks normally. But to Emma, watching from Earth, Stella's time has slowed dramatically. Stella's heartbeat appears to slow. Her movements seem dreamlike and graceful. Her biological processes appear to crawl. This is time dilation in action. The faster Stella moves through space, the slower she moves through time. When 20 Earth years have passed, something miraculous happens. Stella returns home. She lands her spacecraft in the same field where she said goodbye 2 decades earlier. Emma, now 40 years old, rushes to greet her sister. She has lived every day of those 20 years. She has felt every season change. She has celebrated 20 birthdays. But when Stella steps out of her spacecraft, she looks different. Younger. She has aged only about 8 years during her journey. To her, only 8 years have passed. She celebrates what feels like her 28th birthday while Emma celebrates her 40th. The sisters embrace, amazed by time's gentle magic. They are no longer the same age. Stella has become the younger sister, even though they were born at exactly the same moment. This is called the twin paradox, though it's not really a paradox at all. It's simply what happens when two people follow different paths through space-time. Stella experienced less time because she traveled at high speed. Her biological clocks ran slower compared to Emma's. Every process in her body, her heartbeat, her breathing, her cellular division, slowed down by the same amount. From Stella's perspective, her 8-year journey felt completely normal. She didn't feel like she was living in slow motion. She didn't feel like time was strange or different. To her, she aged naturally and normally. It's only when the sisters compare their experiences that the time dilation becomes apparent. This isn't science fiction. This effect has been measured with atomic clocks flown on airplanes. The clocks that traveled showed less elapsed time than identical clocks that stayed on the ground. The difference was tiny, just a few billionths of a second, but it was exactly what Einstein predicted. The faster you move through space, the slower you move through time. It's a fundamental law of our universe. But the twin paradox raises beautiful questions about the nature of time itself. Which sister experienced the real passage of time? Emma, who stayed on Earth? Or Stella, who traveled through space? The answer is both. Each sister experienced time in her own reference frame. From Emma's perspective, 20 years passed. From Stella's perspective, 8 years passed. Both experiences are equally real and valid. There's no universal clock keeping absolute time for the entire universe. Time is personal, individual. Each person carries their own time stream with them wherever they go. This means that aging isn't just about biology. It's about physics. It's about your path through space-time. Two people with identical genes, identical health, identical everything, can age at different rates simply by moving at different speeds or living in different gravitational fields. Time becomes a dimension you can navigate, like the 3 dimensions of space. Move in certain ways through space, and you change your movement through time. The twin paradox shows us that time travel isn't just possible, it's happening all around us. Every person moving at different speeds is traveling through time at slightly different rates. We're all time travelers, following our individual paths through the 4th dimension. Stella aged 8 years while Emma aged 20. In a sense, Stella traveled 12 years into the future. She skipped over 12 years of Earth time by moving fast through space. But this kind of time travel only works in one direction. Stella can't go back to experience those 12 years she skipped. She can't return to the past. She can only move forward through time, sometimes faster, sometimes slower, but always forward. As you lie here in the quiet darkness, imagine the two sisters finally together again. Stella, young and amazed by her journey through space-time. Emma, older but wise from her earthbound experiences. They sit together under the same stars where they were born. They compare their memories of the past 20 years. Emma tells stories of changing seasons, of familiar places growing and evolving. Stella shares tales of alien sunsets and cosmic wonders. Two different paths through time and space. Two different ways of living the same years. Both beautiful. Both real. And now you might wonder, what if you could take a journey like Stella's? What if you could travel not just to distant stars, but to a nearby planet where time flows differently? What would it feel like to live where gravity pulls on time itself in new ways? Imagine standing on a world painted in shades of rust and amber. The sky above you glows a butterscotch color during the day, deepening to blue at sunset. Two small moons hang in the alien sky like distant pearls. The horizon stretches farther than it should, curving gently away under a dome of thin atmosphere. You are on Mars. The red planet. Earth's quiet neighbor in the cosmic dance around our sun. And here, in this alien landscape, time flows differently than it does in your bedroom back on Earth. Mars is smaller than Earth. Much smaller. If Earth were a basketball, Mars would be a softball sitting beside it. This difference in size means Mars has less mass. And less mass means weaker gravity. On Mars, you would weigh only about 40% of what you weigh on Earth. If you weigh 100 pounds at home, you would weigh just 40 pounds on Mars. You could jump higher, run farther, lift objects that would be too heavy on Earth. But the reduced gravity affects more than just your weight. It affects time itself. Remember how gravity curves space-time? How massive objects create wells in the fabric of reality. Mars creates a shallower well than Earth. A gentler curve in space-time. And in this shallower gravitational well, time flows just a tiny bit faster than it does on Earth. The difference is incredibly small. If you lived on Mars for an entire Earth year, you would age about 0.7 seconds more than your friends back home. Less than 1 second over an entire year. But that tiny difference is real. Measurable. And it connects you to the fundamental workings of the universe. Your heartbeat on Mars would keep the same rhythm it always has, from your perspective. Lub-dub, lub-dub, lub-dub. But to someone watching from Earth with impossibly precise instruments, your heart would appear to beat just a tiny bit faster. Not because you're excited or scared or running, but because you're living in a different gravitational field. A weaker curve in space-time itself. This means that Mars is, in a very real sense, a time machine. A place where you would age slightly faster than people on Earth. Where biological processes would tick along at a barely perceptibly quicker pace. The difference is so small that you would never feel it. Your thoughts would flow normally. Your watch would tick at its usual pace. Your breathing would feel natural and easy in Mars' thin atmosphere, assuming you had the right equipment to supply oxygen. But over very long periods of time, the difference would add up. If humans ever establish permanent colonies on Mars, the colonists would age slightly faster than people on Earth. After many generations, this tiny difference might become noticeable. Martian children would grow up in this faster time stream. Their biological clocks would tick in the rhythm of Mars' weaker gravity. They would be time travelers of a sort, living slightly ahead of their Earth-born relatives. But Mars offers other time mysteries too. The planet rotates on its axis almost exactly like Earth does. A Martian day, called a sol, lasts 24 hours and 37 minutes. So close to an Earth day that you would barely notice the difference. But a Martian year is much longer than an Earth year. Mars orbits the Sun more slowly than Earth, taking 687 Earth days to complete one trip around our star. The seasons on Mars last about twice as long as Earth seasons. If you lived on Mars, you would celebrate your birthday less often. You would be younger, measured in Martian years, than you are in Earth years. Time would stretch out in longer cycles of seasons and years. The landscape around you would show the effects of this longer, slower dance around the Sun. Mars has seasons like Earth, but they last twice as long. The polar ice caps grow and shrink over months that stretch into what would be nearly 2 Earth seasons. Dust storms can rage across Mars for weeks, powered by the temperature differences between the long seasons. Some storms grow so large they cover the entire planet, turning the russet world into a globe of swirling amber clouds. Standing on Mars, you would see time written into the very geology around you. Ancient riverbeds carved by water that flowed billions of years ago. Canyons that make Earth's Grand Canyon look small. Volcanoes so tall they pierce through most of Mars' thin atmosphere. Olympus Mons, Mars' largest volcano, stands 13 miles high. It's so tall that if you climb to its peak, you would be above most of the planet's atmosphere. The gravity at the top would be even weaker than at Mars' surface, making time flow even slightly faster. The history of Mars is written in layers of rock and dust that accumulated over billions of years. Each layer tells a story about the planet's climate, its atmosphere, its potential for life. Time made visible in stone and sediment. But perhaps the most beautiful thing about experiencing time on Mars would be the nights. Mars has two tiny moons, Phobos and Deimos. They race across the sky much faster than Earth's moon. Phobos actually orbits Mars 3 times each Martian day, rising in the west and setting in the east. You would see these moons dance through their quick orbits against a backdrop of familiar constellations. The same stars that shine down on Earth would shine down on you, but from a slightly different perspective. Time and space both shifted, creating a new view of the cosmos. From Mars, Earth would be visible as a bright blue star in the night sky, sometimes accompanied by the moon, appearing as a tiny white dot beside the blue one. Your home world, floating in the darkness, where time flows just a tiny bit slower than where you stand. The idea of living on Mars might seem like pure fantasy now. But humans have already sent robotic explorers to walk on its surface. Rovers that experience Mars time, Mars seasons, Mars gravity. Machines that are, in their own way, time travelers living in Mars' faster time stream. Each day, these rovers send messages back to Earth. But the messages take time to travel across the space between the planets. Sometimes just a few minutes, sometimes over 20 minutes, depending on where Mars and Earth are in their orbits. So when we receive a message from Mars, we are hearing from the past. We're listening to news from a different world, sent through space at the speed of light, carrying information across both distance and time. But there's something even more remarkable happening high above both Earth and Mars. Orbiting our planet right now are artificial satellites that experience time differently than you do, proving Einstein's theories every single day. Right now, as you rest in the comfort of your bed, 24 artificial stars circle silently above you. They are not made of burning gas like real stars. They are made of metal and electronics and dreams of human ingenuity. They are GPS satellites, and they are keeping perfect time in their own unique way. These satellites orbit Earth at an altitude of about 12,000 miles above your head. Up there, where the atmosphere is so thin it barely exists, where Earth looks like a blue marble suspended in black velvet, time flows differently than it does in your bedroom. Each satellite carries 4 atomic clocks, the most precise timepieces ever created by human hands. These clocks are so accurate they would lose only 1 second every 300,000 years. They tick away the moments with a precision that borders on the miraculous. But here's something beautiful and strange. Those clocks, racing through space high above you, run fast compared to identical clocks on Earth's surface. Every day, the satellite clocks gain about 38 microseconds compared to clocks on the ground. A microsecond is 1/1,000,000th of a second. An impossibly tiny amount of time. But this tiny difference would make GPS completely useless if scientists didn't account for it. You see, GPS works by measuring time with incredible precision. When you ask your phone for directions, it sends a signal to the satellites above. Each satellite responds, sending back a message that includes the exact time the message was sent. Your phone receives these messages and calculates how long each one took to travel from the satellite to you. Since radio waves travel at the speed of light, your phone can figure out exactly how far away each satellite is. With signals from 4 satellites, it can pinpoint your location anywhere on Earth to within a few feet. But this only works if all the clocks are synchronized perfectly. If the satellite clocks run even slightly fast or slow, the distance calculations become wrong. And wrong distances mean your GPS would think you're somewhere you're not. The 38 microseconds of daily time gain might seem insignificant, but it's not. Light travels about 1,000 feet in a microsecond. So if the satellite clocks were 38 microseconds fast, your GPS would think you were about 38,000 feet away from where you actually are. That's more than 7 miles. Instead of guiding you to your destination, your GPS would send you wandering through fields and forests, completely lost. So every day, scientists adjust the satellite clocks to account for Einstein's time dilation. They slow down the clocks by exactly the right amount to keep them synchronized with Earth time. This correction happens automatically, invisibly, millions of times each day. Why do the satellite clocks run fast? 2 reasons, both predicted by Einstein over a century ago. First, the satellites are moving very fast. They orbit Earth at about 8,700 miles per hour. At this speed, special relativity says their clocks should run slow compared to Earth clocks. This effect would make the satellite clocks lose about 7 microseconds per day. But second, the satellites are high above Earth's surface, where gravity is weaker. General relativity says that weaker gravity makes time run faster. This effect makes the satellite clocks gain about 45 microseconds per day. The net result? The faster time from weaker gravity wins over the slower time from high speed. The satellites gain 38 microseconds daily, which is 45 minus 7. This means that every time you use GPS, you're experiencing Einstein's theories of relativity in the most practical way possible. Your phone is doing calculations that account for the curvature of space-time. It's correcting for the way gravity and motion affect the flow of time itself. The satellites live in their own time stream, slightly accelerated compared to yours. From their perspective, racing through the thin upper atmosphere, their atomic clocks tick at a perfectly normal pace. But compared to you, resting safely in Earth's gravitational embrace, they experience time flowing just a bit faster. It's as if the satellites exist in a slightly different layer of time. Close enough to Earth to serve us, but far enough away to feel the subtle effects of Einstein's curved space-time. Think about this the next time you use your phone to navigate. You're holding in your hand a device that routinely corrects for the relativity of time. A tool that proves, millions of times each day, that time is not absolute. That it flows at different rates in different places. The GPS satellites are like gentle time travelers, circling above you in their faster time stream. They age slightly quicker than you do. Their atomic clocks tick slightly faster than identical clocks in your room. But this difference, properly accounted for, becomes a gift of precise navigation. Without Einstein's insights about time and gravity, GPS would be impossible. The satellites would drift out of synchronization within hours. Your phone would lose track of where you are. The miracle of pinpoint navigation that we take for granted would simply not work. But the satellites do more than just help you find your way. They demonstrate something profound about the nature of reality. They show us that time is woven into the fabric of space itself. That gravity and motion and time are all connected in an elegant cosmic dance. Every navigation request you make sends a small prayer to Einstein's universe. A request that the laws of relativity work exactly as predicted. And they do, every time, with clockwork precision. The satellites circle overhead like a constellation of proof. 24 metal stars carrying atomic timepieces through their own unique layer of space-time. Keeping time in their own reference frame while serving the needs of billions of people in Earth's slower time stream. As you drift toward sleep, imagine those satellites passing silently overhead. Their atomic hearts beating slightly faster than yours. Their clocks marking moments in a time that flows just a bit quicker than the time you experience here on Earth's surface. They are messengers from a realm where time itself is different. Where Einstein's predictions become everyday reality. Where the abstract mathematics of relativity transforms into the practical magic of knowing exactly where you are. But the satellites are not the only place where time behaves strangely. There are regions of space where time doesn't just run a little fast or slow, but where it nearly stops altogether. Imagine a place where time nearly stops. Where seconds stretch into hours, hours into years, years into centuries. Where the very fabric of space-time is stretched so thin that reality itself begins to whisper instead of speak. This place exists. It surrounds the most mysterious objects in our universe. Black holes. A black hole begins its life as a massive star, much larger than our Sun. For millions of years, this star burns brightly, fusing hydrogen into helium in its core. The outward pressure from this nuclear fire balances perfectly against the inward pull of the star's own gravity. But eventually, the fuel runs out. The nuclear fire dies. And gravity wins. The star collapses in on itself with unimaginable violence. All of its mass crushes down into a point smaller than the tip of a pin. This creates a gravitational field so strong that nothing can escape it. Not light. Not matter. Not even time itself behaves normally. The collapsed star becomes a black hole, a region of space where gravity has grown so powerful it warps spacetime into impossible curves. If you could somehow approach a black hole safely, you would witness the most extreme time dilation in the universe. Near the black hole's edge, time slows down dramatically compared to the time you experience here on Earth. Scientists call this edge the event horizon. It's not a physical barrier you could touch. It's more like an invisible boundary in space. Once anything crosses this boundary, it can never return. It falls forever toward the center of the black hole. But from your perspective, watching from far away, something beautiful and strange would happen to anything approaching the event horizon. Imagine an astronaut falling toward a black hole. To her, everything would seem normal at first. Her watch would tick at its usual pace. Her heart would beat its familiar rhythm. She wouldn't feel time slowing down. But to you, watching from a safe distance, she would appear to slow down as she approached the event horizon. Her movements would become more and more graceful, like a dancer moving through thick honey. As she got closer to the point of no return, she would seem to slow down even more. Her gestures would become dreamlike. Her signals to you would arrive more and more slowly. At the very edge of the event horizon, from your perspective, she would seem to freeze almost completely. Her image would hang there, nearly motionless, fading slowly as the light from her form became redder and dimmer. To you, it would appear that she never quite crosses the event horizon. She would seem suspended there forever, frozen at the edge of the black hole like a photograph fading in the cosmic wind. But from her perspective, the experience would be very different. She would feel herself falling normally, crossing the event horizon in what feels like a reasonable amount of time. She wouldn't experience the dramatic slowing that you observe from far away. This is one of the most beautiful mysteries of Einstein's relativity. Two observers can witness the same event and see completely different versions of it. Both experiences are real. Both are correct. Time truly is relative. The massive gravity of a black hole creates the deepest well in spacetime that we know of. Time crawls at the bottom of this well, flowing like thick syrup compared to the time you experience here on Earth. If you could somehow hover just outside the event horizon of a black hole for what felt like an hour to you, and then return to Earth, you might find that years or even decades had passed on Earth while you were gone. You would return to find that your friends had aged while you remained young. You would have traveled forward through time, skipping over the years that pass normally for everyone else. But black holes don't just slow time. They also bend light in extraordinary ways. The strong gravity acts like a lens, focusing and bending the light from stars behind the black hole. If you could look at a black hole directly, you would see a perfect black circle surrounded by a glowing ring. This ring would contain the distorted images of all the stars and galaxies behind the black hole, their light bent around the black hole's massive gravity. Scientists have actually photographed this effect. Using a network of radio telescopes around the world, they've captured images of the black holes at the centers of distant galaxies. The images show exactly what Einstein predicted, a dark shadow surrounded by a bright ring of bent light. These photographs are like looking at the universe's most extreme physics laboratories. Places where space-time is stretched to its limits. Where time dilation reaches its most dramatic extremes. Most black holes are incredibly far away from us. The nearest known black hole is about 1,500 light-years from Earth. That's close enough for astronomers to study, but far enough away that its effects on time don't reach us. But there is a supermassive black hole much closer to home. At the center of our own Milky Way galaxy sits a black hole containing the mass of about 4 million suns. Scientists call it Sagittarius A. Stars orbit this black hole like planets orbit the Sun. But these stars move at incredible speeds, some reaching thousands of miles per second as they swing close to the black hole's edge. Astronomers have watched these stars for years, tracking their orbits with telescopes. The stars' movements follow Einstein's predictions perfectly, proving that massive gravity really does warp spacetime the way the theory of relativity says it should. The study of black holes has taught us that time is far more flexible than we ever imagined. It can slow to a crawl, speed up, or flow at completely different rates in different places. Black holes are laboratories where the universe tests the limits of its own rules. Where time and space bend so dramatically that reality itself becomes dreamlike and strange. As you rest here in the gentle flow of Earth's normal time, remember that somewhere in the cosmos, time moves at every possible speed. From the nearly frozen time at black hole edges to the slightly faster time of high-altitude satellites. But there's another way that time reveals its secrets to us, much closer to home, in the gentle rain of particles that falls from space toward your sleeping form. High above your sleeping form, invisible to your eyes, a gentle rain falls through the darkness. Not raindrops of water, but tiny particles from deep space. They arrive at Earth after journeys that began in distant galaxies, carrying messages from the far reaches of the universe. These cosmic visitors are called cosmic rays. They are mostly protons and atomic nuclei, accelerated to incredible speeds by exploding stars and other violent cosmic events. They race through space for millions of years before reaching our solar system. When these cosmic rays crash into Earth's atmosphere, about 10 miles above your head, something beautiful happens. The collision creates a shower of new particles, born in the thin air high above the clouds. Among these newborn particles are tiny, fleeting things called muons. Muons are like heavy cousins of electrons. They carry the same electric charge as electrons, but they weigh about 200 times more. And they have a secret that reveals one of the most elegant proofs of Einstein's time dilation. Muons live very short lives. If you could somehow create a muon in a laboratory and watch it carefully, it would decay and disappear in about 2 millionths of a second. 2 microseconds. Such a brief existence that they barely have time to exist before vanishing again. This short lifetime creates a puzzle. When cosmic rays create muons 10 miles above Earth's surface, those muons should decay long before they reach the ground. Even traveling at 99% the speed of light, they shouldn't live long enough to complete the journey to where you are. At 99% light speed, a muon could travel about 2,000 feet in its natural lifetime. But 10 miles is over 50,000 feet. The muons should disappear halfway through their fall to Earth. Yet scientists can detect these cosmic muons easily. They pass through the walls of buildings, through rocks, through the Earth itself. Thousands of them pass through your body every minute as you rest here. Most of them complete their 10-mile journey from the upper atmosphere to Earth's surface. How is this possible? How do particles with such short lifetimes manage to travel so far? The answer is time dilation. Einstein's beautiful discovery that time flows differently for objects moving at different speeds. The muons racing toward Earth at 99% the speed of light experience time very differently than you do. From your perspective, resting here in Earth's reference frame, the muons appear to live much longer than their normal 2 microseconds. Time slows down dramatically for the fast-moving muons. What feels like 2 microseconds to a muon actually lasts about 14 microseconds from your perspective on Earth. This gives them enough time to complete their journey from the upper atmosphere to the ground. From the muon's perspective, something equally interesting happens. To the muon, its lifetime feels perfectly normal. 2 microseconds pass at the usual rate. But the distance it needs to travel appears much shorter due to length contraction, another effect of relativity. The 10-mile journey that you measure appears as only about 1.4 miles to the fast-moving muon. So from the muon's point of view, it lived its normal lifespan while traveling a much shorter distance. Both perspectives are correct. Both are real. Time dilation and length contraction work together to allow the muons to complete their cosmic journey. This happens thousands of times every second, all around the world. Cosmic rays create muons in the upper atmosphere. The muons race toward Earth at incredible speeds. Time dilation allows them to survive the journey. They pass through buildings, mountains, and people, carrying their proof of Einstein's relativity with them. You are sitting in a constant, gentle shower of these time-dilated particles. Each muon that passes through you is a tiny messenger from Einstein's universe. a living demonstration that time really can slow down for fast-moving objects. Scientists use this muon rain as a natural laboratory for studying relativity. They place detectors at different altitudes on mountains. The detectors at the top catch newly created muons. The detectors at the bottom catch muons that have survived the journey down the mountain. By comparing how many muons are detected at different heights, scientists can measure time dilation directly. The results always match Einstein's predictions perfectly. Some of the muons that reach Earth's surface continue their journey underground. They pass through rock and soil, gradually losing energy and slowing down. Eventually, they decay in the deep Earth, their cosmic journey finally complete. A few muons are captured by atomic nuclei before they decay. When this happens, the muons spiral into the nucleus, replacing electrons in atoms. This creates exotic atoms that exist for just brief moments before the muon decays from within. These cosmic messengers connect you to the far reaches of space and time. The proton that started as a cosmic ray might have been accelerated by a supernova explosion thousands of light-years away. It traveled through the galaxy for millennia before reaching Earth's atmosphere and creating the muons that pass through you now. Each muon carries within its brief existence a story of relativity in action. Its extended lifetime is proof that time can stretch. Its journey from sky to Earth is evidence that the universe operates according to Einstein's elegant mathematics. The muon rain is invisible and silent. You cannot see or feel these particles as they pass through you. But they are there, constantly arriving from above, carrying their message about the nature of time itself. They remind us that we live in a relativistic universe. A place where time is flexible, where simultaneity is relative, where the simple act of motion can stretch moments into longer moments. The cosmic ray showers happen day and night, in all weather, in every season. The muons fall like gentle, invisible snow, each one a tiny proof that Einstein was right about the deepest workings of reality. As you rest here in the darkness, remember that you are not alone. You are accompanied by countless tiny visitors from space. Particles that have experienced time dilation in their race from the upper atmosphere to your room. They pass through you carrying their stories of relativity. Evidence that time really can slow down. Proof that the universe is stranger and more beautiful than it appears on the surface. But time dilation isn't just something that happens to exotic particles from space. It's something that touches your everyday life in subtle ways, creating tiny changes in the rhythm of your own existence. You have been a time traveler your entire life. Not in the dramatic way of science fiction movies, but in the quiet, elegant way that Einstein discovered. Every moment of your existence, you move through time at your own unique pace, shaped by your motion through space and your position in Earth's gravitational field. Right now, as you lie here breathing softly, your personal time stream flows at the gentle rhythm of someone at rest near Earth's surface. Your heart beats about once per second. Your cells divide on their ancient schedules. Your atoms vibrate at frequencies set by the fundamental constants of nature. But this rhythm changes throughout your day in ways so subtle you never notice them. When you wake up tomorrow morning and place your feet on the floor, you will experience a tiny shift in time's flow. Your feet, now closer to Earth's center, will enter a slightly stronger gravitational field. Time will slow for them by an infinitesimal amount compared to when you were lying flat. The difference is impossibly small. About 22 billionths of a nanosecond per second. But it's real. Your feet age more slowly than your head when you stand up. The effect is so tiny that even the most sensitive atomic clocks can barely measure it, but Einstein's equations predict it perfectly. When you walk across your room, you become a time traveler in motion. Each step carries you through space at a few miles per hour. This motion creates time dilation, slowing your personal clocks by an amount so small it exists only in the realm of theory. But the mathematics are clear. Motion through space affects motion through time. If you climb the stairs in your house, something more interesting happens. As you rise higher, you move farther from Earth's center. The gravitational field grows slightly weaker with each step. Time begins to flow a tiny bit faster for you. By the time you reach the second floor, you have entered a time stream that flows about 6 parts in a trillion faster than the ground floor. Over the course of a human lifetime, this difference would amount to less than 1 second. But it demonstrates a profound truth about the nature of time itself. Time is not a universal constant. It flows like a river with currents and eddies. Every floor of every building exists in its own barely perceptible layer of time. The penthouse of a skyscraper experiences time slightly faster than the lobby. The basement flows slightly slower than the ground level. When you ride in an elevator, you travel through these layers of time. Rising up carries you into faster time streams. Descending brings you into slower ones. The elevator becomes a time machine, moving you not just through space but through the subtle variations in time's flow. But the most dramatic time dilation in your everyday life happens when you travel. When you ride in a car moving at 60 miles per hour, your biological clock slows down compared to someone standing still. The effect is incredibly tiny, but it's there. You age slightly more slowly during your commute than you would sitting at home. Flying in an airplane creates even more interesting time effects. Commercial jets cruise at about 500 miles per hour and at altitudes around 35,000 feet. Both the speed and the altitude affect your personal time stream. The motion of the plane slows your clock slightly due to special relativity. But the high altitude, where Earth's gravity is weaker, speeds your clocks up due to general relativity. At typical cruising altitudes and speeds, the gravitational effect wins. You actually age slightly faster while flying than you do on the ground. Scientists have measured this effect with atomic clocks flown on commercial flights. The airborne clocks run fast compared to identical clocks left on the ground, gaining about 273 nanoseconds during a typical cross-country flight. This means that frequent flyers experience time slightly differently than people who stay earthbound. Flight attendants and pilots, over the course of their careers, accumulate tiny amounts of extra aging due to their time spent in high-altitude, fast-moving time streams. The differences are far too small to affect human health or lifespan in any noticeable way. But they demonstrate that your personal experience of time depends on how you move through the world. Every choice you make about where to go and how fast to travel subtly affects your journey through the fourth dimension. If you could somehow run at the speed of sound, about 767 miles per hour, your time dilation would become slightly more significant. You would age about 1 second less per year compared to someone standing still. Still tiny, but a step toward the dramatic time effects that become possible at very high speeds. Athletes experience minute time dilation effects during their competitions. A marathon runner, maintaining about 12 miles per hour for over 2 hours, ages about 1 trillionth of a second less than spectators watching from the stands. Race car drivers, reaching speeds over 200 miles per hour, experience slightly more time dilation during their races. Even the rotation of the Earth affects your personal time stream. If you live near the equator, you're moving faster through space due to Earth's rotation than someone living near the poles. The equatorial speed is about 1,000 miles per hour. This motion creates a tiny time dilation effect that makes people at the equator age slightly more slowly than people at the poles. The difference amounts to about 5 billionths of a second per year. Over a human lifetime, equatorial dwellers age about 0.3 microseconds less than polar inhabitants. A difference so small it's purely theoretical, but a reminder that even Earth's rotation affects the flow of time. Your body carries with it the accumulated effects of every journey you've ever taken. Every airplane flight, every car ride, every walk up a hill has left its mark on your personal timeline. You are the sum of all the time streams you've experienced. The remarkable thing is that you've never felt any of these effects. Your heart has always seemed to beat at the same pace. Your thoughts have always flowed at their normal speed. Your watch has always appeared to tick normally. This is because time dilation affects everything equally. When your biological clocks slow down, your mental processes slow down by the same amount. When time speeds up for you, all of your internal rhythms speed up together. You remain synchronized with yourself, even as your time stream shifts relative to the outside world. You are like a fish swimming in the ocean of space-time, always feeling the water temperature as normal, even as you move between warmer and cooler currents. Your personal experience of time always feels constant and natural, regardless of how it appears to outside observers. But these tiny variations in time's flow connect you to the grandest scales of the universe. They link your everyday experiences to the exotic physics of black holes and neutron stars. They make you a participant in the cosmic dance of space and time that Einstein first glimpsed over a century ago. Every step you take writes a story in the language of relativity. Every journey you make traces a path through the fourth dimension. You are both author and character in the ongoing narrative of space-time itself. And as you prepare to drift into sleep, your body will enter its own unique time stream of rest, where dreams unfold in the gentle rhythm of a mind at peace with the eternal dance of time and space. Here, in the quiet darkness of your room, you rest at the center of the most beautiful dance in the universe. The eternal waltz of space and time. A cosmic choreography that began with the first moment of creation and will continue long after the last star fades to darkness. Your heartbeat keeps time with this ancient rhythm. Lub-dub, lub-dub, lub-dub. Each pulse marking another moment in your personal journey through the fourth dimension. Each breath carrying you forward through space-time at exactly 1 second per second, as measured in your own reference frame. But you are not a passive observer of this dance. You are a participant. Every movement you make, every position you occupy, every speed at which you travel, changes your relationship with time itself. You bend space-time around you, just as it bends around you. Your body, though small compared to planets and stars, has mass. And mass curves space-time. The effect is tiny, impossibly small, but it's real. Einstein's equations make no exceptions for size. Every particle, every atom, every cell in your body contributes to the gentle curvature of reality around you. You create your own gravitational field. Weak beyond measurement, but mathematically identical to the fields created by Earth, by the Sun, by distant galaxies. The same equations that describe the motion of planets also describe the space-time around your sleeping form. In this way, you are connected to everything in the universe. The same fundamental forces that guide the dance of galaxies also flow through your blood, pulse in your neurons, vibrate in your atoms. You are made of star matter, following star laws, participating in the same cosmic symphony that plays across all scales of space and time. The oxygen in your lungs was forged in the nuclear furnaces of ancient stars. The carbon in your cells was created when massive suns collapsed and exploded, scattering their treasure of heavy elements across space. The calcium in your bones, the iron in your blood, the phosphorus in your DNA, all of it born in stellar fire billions of years ago. You are not just in the universe. You are the universe becoming aware of itself. A collection of cosmic matter organized into consciousness, capable of pondering its own origins and destiny. And through it all, time flows. The mysterious fourth dimension that allows change to occur, events to unfold, cause to follow effect. Without time, the universe would be frozen, static, eternal but empty of story or meaning. Time gives the cosmos its narrative structure. Its past, present, and future. Its beginning, middle, and whatever ending awaits in the far distant future. Time transforms a collection of particles and forces into a living, evolving, creative universe. As you drift towards sleep, your brain waves begin to slow. The rapid oscillations of waking consciousness give way to the deeper rhythms of dreams. Your body temperature drops slightly. Your breathing becomes more regular. Your heart rate settles into the peaceful pace of rest. In sleep, you will experience time differently than you do while awake. Dreams can seem to last for hours while only minutes pass in the waking world. Or they can compress years of imagined experience into brief moments of REM sleep. The brain creates its own relationship with time, separate from the clocks that measure physical duration. But even as you sleep, the cosmic dance continues around you. The Earth rotates on its axis, carrying you through space at over 1,000 miles per hour. The Earth orbits the Sun at 67,000 miles per hour. The solar system moves through the galaxy at 514,000 miles per hour. The galaxy itself races through space at over 2 million miles per hour. You are traveling through the universe at incredible speeds, even as you lie perfectly still in your bed. Motion and rest are relative concepts, dependent entirely on your frame of reference. From the perspective of someone on a distant star, you are moving at tremendous velocity. From your own perspective, you are peacefully at rest. This is the elegant truth that Einstein discovered. Reality depends on the observer. Space and time are not absolute stages on which events play out. They are dynamic, flexible, responsive to matter and energy and motion. They dance together in perfect partnership, creating the four-dimensional theater in which all existence unfolds. The story of time dilation is ultimately the story of your place in this cosmic dance. You are both infinitely small and infinitely significant. A brief arrangement of atoms that can contemplate eternity. A temporary pattern of matter and energy that can understand the fundamental laws governing all patterns everywhere. Your journey through space-time is unique. No one else will follow exactly the same path through the four dimensions. No one else will experience precisely the same sequence of moments, the same collection of time streams, the same personal relationship with the flow of time. You are writing your own story in the language of relativity. Each day, each choice, each movement creates another sentence in your personal narrative of space and time. And tonight, as sleep carries you into dreams, you continue this eternal dance, moving forward through time at the gentle pace of rest, your heartbeat keeping rhythm with the cosmos itself.